Hi everyone, welcome back to Chem Story. Today we're diving into how alkynes react with water when a mercury catalyst is involved. It's an important reaction because it gives us ketones. So in this lesson, we'll break down exactly how that transformation works, step by step. Let's get started. Alright, let's start by taking a big picture look at how this reaction works. When a terminal alkyne reacts with water, and you've got both mercuric sulfate and sulfuric acid in the mix, something pretty interesting happens. Water adds across the triple bond, and that gives us an enol intermediate. But here's the thing. Enols don't stick around for long. They rearrange pretty quickly through something called tautomerization, and that's how we end up with a ketone. Now, one key feature of this reaction is regioselectivity. It follows Markovnikov's rule, which means the OH group ends up on the more substituted carbon of the triple bond. So just to sum it up real quick, mercury-catalyzed hydration of alkynes gives you ketones, and it happens through an enol intermediate that rearranges automatically. Alright, let's walk through the mechanism for mercury-catalyzed hydration, one step at a time. Step 1. The pi electrons from the alkyne attack the mercury ion, Hg2+. That creates a new bond between one of the carbons and the mercury, and the other carbon ends up as a vinyl carbocation. In step 2, water comes in as the nucleophile. It attacks that carbocation and adds on as an H2O group. Then in step 3, one of the protons on that water group drops off. That leaves behind a neutral OH, and now we've got an enol on our hands. Next, in step 4, we get rid of that mercury group. Under acidic conditions, a proton comes in and takes its place, so the Hg+ gets replaced with a regular hydrogen. And finally, we've got step 5, tautomerization. This is where the enol rearranges to form the final product. The double bond shifts over, the OH turns into a carbonyl group, and the hydrogen moves to the carbon next door, converting the enol into a stable ketone. So that's the whole mechanism. 5 simple steps that take us from an alkyne all the way to a ketone. Here's the full breakdown of how the mechanism works, step by step. We start with a terminal alkyne, and in the very first step, the triple bond attacks the Hg2+ ion. That forms a bond between the alkyne and the mercury, and at the same time, we get a vinyl carbocation, specifically on the more substituted carbon. Then, in step 2, water comes in as the nucleophile. It attacks the carbocation and adds an H2O group to that position. In step 3, one of the protons on that water group gets removed. That gives us a neutral OH group, and now we have the enol intermediate. But here's something to keep in mind. The enol still has a mercury group hanging on. So in step 4, a proton from the acid comes in and kicks that out, swapping the Hg2+ for a hydrogen. At this point, we've got a neutral enol, but enols aren't stable. So we move into step 5, tautomerization. In this step, the double bond shifts, the OH group becomes a carbonyl oxygen, and a hydrogen moves over to the carbon next door. And that's it. We've got a ketone as our final product. This whole process follows Markovnikov's rule, and it's smooth, reliable, and super useful in synthesis. Now let's finish up by looking at what kinds of products this reaction actually gives, and how regioselectivity plays into that. If you're working with a symmetric internal alkyne, both sides are the same. So the hydration gives you just one ketone. There's only one place the OH can go, which makes the outcome super straightforward. But if the alkyne is asymmetric, now you've got 2 different ends. That means the enol can form in 2 ways, so you end up with a mixture of 2 isomeric ketones. Now here's the cleanest scenario. When you start with a terminal alkyne, in that case, the reaction gives you one clear product, a methyl ketone. And that's because the OH always adds to the more substituted carbon, exactly what you'd expect from Markovnikov's rule. So there's no mixture, no surprises, just one predictable outcome. Alright, that wraps up our deep dive into mercury-catalyzed hydration of alkynes. We walked through the full mechanism, saw how the enol forms and rearranges, and looked at how this method gives you clean ketone products, especially when you're working with terminal alkynes. Thanks so much for watching, and as always, I'll see you in the next Chem Story video.